everyone, I'm Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. Today we are going to discuss topic related to optics. We know what is optics. Optics is a branch of science which deals with different phenomena exhibited by light. And of course, we have seen that different phenomena exhibited by light, it can be reflection, refraction, so transmission. And apart from that, very important application point of view, and we are talking very important phenomena exhibited by light are interference, diffraction, and polarization. And we know that these particular phenomena, they are very much useful in our day-to-day life. Okay, in terms of application point of view. Now today we are going to discuss one application related to interference. How interference phenomena it can be used in order to find a wavelength of a given source. Also how we can find refractive index of a given liquid. So what we'll do first, we'll have introduction about the interference and that interference pattern, how it gives rise to Newton's rings. So how circular rings are formed and how these circular rings are going to help us for application, we are going to discuss today. So here, today our topic of discussion is Newton's rings. And these Newton's rings, they are completely based on phenomena of interference exhibited by light. So what is interference? We know that phenomena of interference, it is based on principle of superposition of waves. What is principle of superposition of waves? Suppose if at a time we have many number of waves, suppose many waves are traveling, and if we have many number of waves going through a medium, then what we'll observe here is the resultant displacement due to superposition of all these waves in a certain medium, it is given by algebraic sum of displacements due to individual waves. So when waves are overlapping each other, then resultant displacement in that particular medium will be because of displacement of each wave. We have to take into consideration algebraic sum of displacements due to each wave. Suppose I have taken two waves. Suppose one wave displacement it is given by y1 and another wave displacement if it is given by y2, then according to principle of superposition of waves, the resultant displacement it is given as algebraic sum of y1 and y2. So what is y1? Y1 is displacement due to individual wave. Suppose if we call that wave as 1. And what is y2? Y2 is displacement due to second wave and that we are calling it as 2. And in that region, because of overlapping of these two waves 1 and 2, the resultant displacement will be nothing but algebraic sum of these two displacements y1 and y2. And when we'll use plus sign is used when these two waves are traveling in the same direction and when they are in phase. When they are maintaining phase, actually we'll say that when these waves are coherent. And when we'll use minus sign, when these two waves are traveling in opposite direction and when these waves are not incoherent with each other. So coherent is going to play very important role when we are talking about phenomena of interference. So now, as I told you, interference it is based on principle of superposition of waves. So what is principle of superposition of waves? Just now we have discussed. Now we have to define interference. Now, according to interference, what we are saying here is, of course, we'll take into account this resultant displacement, which is algebraic sum of displacements due to individual waves. So what you will observe here is resultant intensity is also because of algebraic sum of intensity due to individual waves. So when two or more waves get superimposed in a region, then in that region, what we'll observe here is the resultant intensity it will get modified. And how a resultant intensity will get modified? That intensity, it can be the sum of intensity due to individual waves or it can be difference of intensities due to individual waves. And when we'll take sum of intensities due to individual waves, then that type of interference, it is called as constructive interference. And that constructive interference, it will give rise to maximum intensity and that maximum intensity will give rise to bright fringe. Whereas In case if a resultant intensity in the region of superposition is difference of intensities due to individual waves, then that type of interference, it is called destructive interference. And destructive interference will give rise to minimum intensity, and this minimum intensity again it will give rise to dark fringe. So here what we'll observe here in case of interference, we'll get alternate bright and dark fringes. And in case of interference, we'll observe that all dark fringes, they are of same intensity. Actually, we'll say that dark fringe and bright fringes, they are of same width. And that width is nothing but our fringe width. And this fringe width we can calculate, and for that we have our Young's double slit experiment. So based on Young's double slit experiment, we know how the intensity can be calculated and what are the conditions for maximum and minimum intensity. We know that when like waves, when they will be in phase, we know that condition for maximum intensity, when we are discussing about those conditions, we have seen that for maximum intensity, path difference should be integral multiple of lambda. Whereas for minimum intensity, we know that what is the path difference? Path difference is what we'll observe here is half integral of lambda beta. So here, based on these conditions, we'll have maximum and minimum intensity. So if path difference is integral multiple of lambda, then in that case, we'll have maximum intensity, that is nothing but constructive interference. Whereas if our path difference is half integral multiple of lambda, then it will give rise to minimum intensity. So this is the conditions in order to get maxima and minima. And by taking these conditions, we can get the width of bright and dark fringes. And we have observed that all dark and bright fringes, they are of same width, and that is nothing but the fringe width. So now we are going to use this concept of interference and also these conditions for maxima and minima in our today's experiment, which is nothing but Newton's rings experiment. And what exactly is this Newton's rings experiment? And this experiment, it is completely based on phenomena of interference. And here what we are doing here is generally we'll make light fall on a film, thin film. Here we are talking about a thin film. What do you mean by thin film? So here we'll take a medium. It can be a glass medium. It can be a liquid medium. So that medium, it can be any material. But thickness of that film, it should be uniform. So here we'll take a film whose thickness is of course not only uniform. Actually thickness of that particular film should be very, very small. So we can have uniform thickness of the thin film, or we can have non-uniform thickness of that film. But what we have to maintain, most important point, we have to maintain that thickness of the film should be very, very small. What happens when we make light fall on such film? Then we'll observe that suppose if I take a film like this, so in that case, suppose I have taken a glass film. Okay, so here in this case, light, if I make light fall on this film which is made up of the glass, this is my glass material, and if you observe that particular glass, it has got refractive index mu and thickness of the film is T, and in our case T should be very, very small. And if we make our light fall on such glass film, then what you will observe here is your light, it gets reflected from top surface of the film, and also you will have light entering the film and then again getting reflected from the bottom surface of the film. Now we have two light rays, one light ray getting reflected from top surface of the film and another light ray which is getting reflected from bottom surface of the film. And due to interference, due to superposition of this light reflected from top and bottom surface of thin film, we'll get one pattern, and that particular pattern we are going to study in case of this Newton's rings. But in this case, of course, till now I have discussed about a film which is of uniform thickness, but in Newton's rings we are going to take a film which is non-uniform. So here we are considering non-uniform thin film. Okay, and in order to form that non-uniform thin film, what we are going to do here, if you see this experimental arrangement here, first what we are going to do, this is our plano convex lens. Okay, so first we are going to take plano convex lens, and then we are taking a plain glass plate. So plano convex lens, and as well as we are taking plain glass plate. And next what we are doing, we are keeping this plano convex lens with its convex surface on this plain glass plate, so that this lens and glass plate, they are in contact at point O. So we are keeping our convex lens on a plain glass plate such that point of contact between the bottom, that is convex surface of this plano convex lens, and this top surface of plain glass plate, they are in contact at point O. And if you keep this setup, plano convex lens and the plain glass plate, if we keep it in open air, obviously this area, whatever area is formed below this convex surface and the plain glass plate, top of plain glass plate and below the convex surface of plano convex lens, what you will observe here is that particular area, it will be filled by air. So here there will be formation of air film. Where air film is being formed? Air film is formed between the convex lens of this plano convex lens and the top surface of the plain glass plate. And you will observe that thickness of this film will be very, very small. Because we know that curvature of convex lens, it will be very, very small. And of course, we are keeping it on a plain glass plate. So here thickness of film that is formed between both will be very, very small. And here it's not an uniform film. So of course air film is formed, but it is not of uniform thickness. What you will observe here is thickness of this air film at the point of contact is 0. And as we are moving away from the center of this particular point of contact, thickness of air film, it is gradually increasing. So what you will observe here is thickness of the air film keeps on increasing from the point of contact, which will give rise to non-uniform thin air film. So our whole intention behind this setup is to form non-uniform thin air film. And what we are going to do here is that particular air film, we have to expose it to light. So we have to make light fall on such air film. For that, what I am doing, I am taking a monochromatic source. Here we'll have a source. What do you mean by monochromatic source? Source which has got single wavelength. So I'll take monochromatic source, and light from that monochromatic source, using our lens, we are going to make it fall on another plain glass plate. And how this plain glass plate is held? It is held at 45 degrees inclination. So as you can see in this figure, this particular plain glass plate is held at 45 degrees inclination. And why we kept our plain glass plate at 45 degrees inclination? Our intention is when light goes and falls on this plain glass plate, then from this plain glass plate, our light get reflected onto this air film normally. So we are going for normal incidence of light. So we have to make our light fall normally on this air film which is formed between the convex surface of the lens and the plain glass plate. Okay, so for that we are keeping this, we are making use of this glass plate. Now once your light falls normally means where angle of incidence I is equal to 0 as well as angle of reflection R is equal to 0. So angle of incidence as well as angle of reflection will be 0. And what we'll observe here is when our light falls on this air film, then what you will observe here is we are interested only in reflected light. Here we are going to discuss Newton's rings in reflected light. It means that we are interested in the light reflected, and from where it should get reflected, as we have taken in the last case, light, it should get reflected from top and bottom surface of the air film. Now if you see our figure here, again I am drawing it. This is our convex lens and this is our plain glass plate. Now suppose light is entering this lens and then it goes inside. Now this is the top surface of the air film. Now our light, it gets reflected. As you can see here, this is our first ray which got reflected from top surface of the air film. Now from this point, light, it goes through the air film. And then again at this bottom surface of the air film, our light, it will get reflected and it will come out like this. So now I got two reflected rays, 1 and 2. And from where these light got reflected, as you can see, ray 1, it is coming from the top surface of air film, and ray 2, it is coming from bottom surface of air film. Now this light which got reflected from top and bottom surface of the air film, they'll superimpose. So superposition of light waves reflected from top and bottom surface of air film which is of non-uniform thickness and which is formed between the lens and the glass plate will take place. As a result, interference phenomena will takes place. And we know what will happen once interference takes place. Because of constructive interference, we'll get bright fringe. Because of destructive interference, we'll get dark fringe. Now, how to observe those fringes? For that, we are taking help of this optical instrument, and this optical instrument, it is called as microscope. So, what we'll do? We'll view this particular light coming out from this particular setup through the microscope. Now those reflected light, they'll enter microscope, and if spectator is going to see through that microscope, he will be able to see, of course, bright and dark fringes. But what is the shape of fringe in this case? You will observe that in this case, shape of fringe is circular. So you have circular, alternate, bright and dark fringes. And why we are getting circular fringes? So why? Because as you know, what is the shape of the air film that is formed between the convex surface as well as plain glass plate? Shape is circular. Why? Because we are keeping convex surface, and we know that below that convex lens the shape is circular. So actually we can say that just you try to imagine a sphere. And if we cut a sphere down a small part, that's down part, it will be circular in shape. And the circular shape, because it is kept on the plain glass plate, so here, there, what you will observe here is shape of the air film will be circular. And because our air film is circular, that's why even our fringes are also circular in nature. And these circular rings, alternate, circular, bright and dark rings, are nothing but our Newton's rings. And why they are called Newton's rings? After the name of the scientist who has performed this experiment and who has observed these circular rings. So this is the whole experimental arrangement to see how Newton's rings can be formed. So what exactly happened in this experiment? What we have done, first we tried to make an air film of non-uniform thickness. For that we have taken help of lens and glass plate. So once we kept our convex lens on a plain glass plate, then below there will be formation of circular air film, of course, whose thickness will be gradually increasing when we move from point of contact of lens and glass plate. And if we expose this air film to light, and that light, it should fall normally. In order to make that normal incidence of light, we are keeping one glass plate held at 45 degrees inclination in the path of light. And once we go for normal incidence, we'll collect all those light rays which got reflected from top and bottom surface of the film. And when we view through the microscope, we'll be able to see alternate circular, bright and dark fringes. So these will give rise to formation of Newton. So what is the main phenomena of light observed here? Interference. Now we'll see what different parameters we can obtain from this Newton's rings experiment and how they are going to help us in application. So this is our experimental arrangement as I have just discussed. So we have our convex lens of radius of curvature, and here convex lens is kept with its convex surface on plain glass plate. Now they are at point of contact 0 where thickness of the film is 0. Then we are keeping one more glass plate held at 45 degrees inclination with respect to this monochromatic light, so that we can make our light fall normally on this air film. And once we get reflected light, we are going to collect light reflected from curved surface, and of course light which got reflected from the plane surface of the plate. So these reflected rays, they are going to undergo interference, giving rise to circular fringes, and these fringes we are going to, these rings, particular rings, circular rings, we are going to observe the optical instrument called as microscope. Now next, once we got this interference pattern, as you can see this figure already I have explained. So we are totally considering ray 1 and ray 2. As you can make out that ray 1, it is coming from the point B. And what is our point B? This point B is nothing but our top surface of air film. And again at this point, as you can see that from this, of course, point B, light, of course, part of it got reflected and it has come out as ray 1. And at the same point B, light, it is getting transmitted through the air film, and then it is striking the top surface of the plain glass plate, and again it got reflected, it is passing through the lens and it is coming out as ray 2. So because of interference between ray 1 and 2, we are going to get interference pattern. And here now we have next step is what we are going to do, we are going to see what is the condition for that particular ring to be bright and what should be the condition for that ring to be darker. And for that, what we are going to do here is, here we are going to take into consideration Stokes theorem. And we know that what is Stokes theorem. According to Stokes theorem, when your light gets reflected from a surface backed by denser medium. So here you can make out this our lens, it is of glass, and whereas this film which is made up of air, and we know that this air is rarer medium compared to glass medium. So for air medium, of course, refractive index is 1, whereas for glass medium it is around 1.5. So glass is more denser than air. So here we are taking the light. Suppose if you take this particular, suppose we are talking about this ray 1, and at this point, as you can make out, that ray is traveling from denser medium to rarer medium. So in that case, what you will observe here is, generally light, it will go under extra phase change. And what is that extra phase change? It is given by pi. And it will travel additional path change of lambda by 2. So either it goes additional phase change of pi or additional path change of lambda by 2. So we have to take even the Stokes theorem also into consideration. And when we proceed further, what you will observe here is, see, already we have discussed that like when we have discussed about interference in thin films, there we have taken the thin film which has got uniform thickness, and in that case our path difference, it came out to be 2 mu t. So this is the case when we have taken our thin film, and there we have observed here is path difference is equal to 2 mu t cos r plus lambda by 2. What is mu? Mu is refractive index of the medium which we are taking. Of course, in our case, it is air film. So we can conveniently take it as 1. And if you take glass, then we have to consider refractive index of the glass. And what is T? T is thickness of the air film. But in our case, air film thickness is not constant. And what is R? R is angle of refraction. So angle of refraction in the film, in that particular thin film. And of course, why we are adding this plus lambda by 2, just as I told you, when light travels or when it gets reflected backed by a denser medium, then in that case it suffers additional phase change of pi or additional path difference of lambda by 2. That's why I have to add this plus lambda by 2. Now this particular path difference, we are going to use it in our Newton's rings experiment. And as I told you, in our case it's say air film, so that's why its refractive index will be 1. And we are going for normal incidence, and for normal incidence, what you know, that angle of reflection and angle of refraction, both of them will be equal to 0. So in this formula for path difference, I am going to substitute angle of refraction to be 0, as well as refractive index of the air film, I will take it as 1. Then what will be our path difference? This path difference, it comes out to be 2t plus lambda by 2. So this is our path difference now. Okay, now first, I am going to take this point of contact. So if you go to this point of contact, this particular point O, what is the thickness of the air film? Thickness of the air film is 0. So what you will observe here is, once I substitute t is equal to 0 in this path difference, so I end up having path difference to be lambda by 2. And we know that once your path difference is half integral multiple of lambda, then it is condition for minima. So as you can see, we are getting path difference as lambda by 2. It means that it is satisfying condition for minimum intensity. So which gives rise to dark fringe. So it means that at the point of contact, whatever ring, circular ring is formed, it is a dark circular ring. That's why if you observe Newton's rings through the microscope, central spot will be dark, and central spot will be dark only if you consider interference of light reflected from top and bottom surface of air film. Whereas if we consider interference due to light transmitted from top and bottom surface of air film, then in that case our central spot will be bright. So these are completely different from each other. So in our case, because we are considering only reflected light, in reflected light we will observe that our central spot is dark. And why our central spot is dark? Because it is satisfying condition for path difference, which comes out to be lambda by 2 as thickness of the air film is 0. So here we are very much clear that our central spot is dark. Now next, I'm going to take this path difference 2t plus lambda by 2. Now I'm going to apply condition for maxima and then condition for minima. Now what is the condition for maxima? The condition for maxima is path difference should be equal to n lambda. I told you for maxima path difference should be n lambda, and for minima path difference should be 2n plus 1 lambda by 2. So here, if path difference is n lambda, and if we rearrange the terms, then finally we end up having for bright fringe 2t is equal to 2n minus 1 into lambda by 2. This is the condition in order to get bright ring. Whereas similarly, the condition for dark ring is path difference, it should be equal to 2n plus 1 lambda by 2, as I told you earlier. And if we rearrange the terms, finally what condition we'll get for dark ring? 2t should be equal to n lambda. So these are the conditions for bright rings and dark rings. And we are going to use these conditions for bright and dark rings in order to find diameters of bright and dark rings. So that we are going to do it next. Now for that, what I have done in order to find, so now our intention is to find diameters of bright and dark rings. So we are trying to find diameters of bright as well as dark rings. So dark circular rings. So for that, what we are going to do, as you can see here, what I have done, suppose this is our lens, this is our plano convex lens, and I have extended this lens so that it forms a circle. When we extend this convex lens, then we'll get a circle whose center is at C. So here we are getting center at C. Okay, and we are saying that let R be the radius of curvature of this particular lens. If R is radius of curvature, then obviously this part it will be R. Now if you take this lens, I am considering one region here. This is our region. At this region, what is the thickness of the film? I am taking it as T. See here I am selecting 2 points A and B. At these 2 points A and B, what is the thickness of the air film? Thickness of the air film is T. Let us suppose that at these points A and B, see here we know that how the rings will be formed. Central spot will be dark. It will be followed by alternate bright and dark rings. So here, suppose at this point A and B, I am getting one circular ring. Now let us suppose that R be the radius of that circular ring which is formed at point A and B, where thickness of the film is T. Okay, so we'll take all this into consideration. So if you take this figure, you will observe that this particular NA it is R, even NB it is also R, and thickness of the film is T here, and this part is nothing but radius of curvature of the lens R. Now I'm going to use property of the circle. Now from the property of the circle, what we have here is this. Here we have two chords intersecting each other at the point N. Okay, so here in this circular, which is extension of this lens, we have one point N. What is this point N? Which is intersecting two chords passing through the circle. And in such case, what you will observe here is this NA into NB will be equal to, I am talking about this particular property of circle, NA into NB, it will be equal to ON into ND. And what is our NA and NB? Both of them, they are R into R, which is nothing but radius of circular ring at points A and B. Okay, and then what is ON? ON is nothing but our thickness of air film T. And what about ND? See, this is R and this is also R. So this total is 2R, and from this I have to take out this particular part which is nothing but thickness of the air film. So that's why we'll get 2R minus T. And if we rearrange the terms, we'll end up having thickness of the air film. See, we are neglecting T square in this because T square is very, very small. We are taking thickness of the air film to be very, very small. And if we square it, that value will be still smaller. Suppose if thickness of air film is 0.1, then if we square it, we end up having 0.01. So it will be very, very small value. Just for simplification, we can neglect this term. So we got this thickness of the air film in terms of radius of circular ring as well as radius of curvature. And this particular thing I am going to use in order to find diameter of bright and dark ring. What is the condition we got for bright ring? 2t is equal to 2n minus 1 lambda by 2. So in place of t, I am going to substitute this particular formula which we just got for thickness. And if we rearrange the terms, I will get radius like this. And we know that radius can be written as half of the diameter. If I substitute, I end up having diameter of bright ring like this. So it means the diameter of bright ring is proportional to square root of 2n minus 1. But what is 2n minus 1? It is nothing but odd natural number. So one important point what you have to observe here is diameter of bright ring is proportional to square root of odd natural number. Similarly, for dark ring, we'll observe that what is the condition for dark ring? 2t is equal to n lambda. So in place of thickness, I'm going to substitute again r square by 2r. If I simplify, I'll get r square to be n lambda r. Here we are talking about radius of dark ring. And if I substitute in place of radius, half of the diameter, I end up having this formula, and this formula is very, very important. This formula we are going to use for application in order to find wavelength of light as well as refractive index of the liquid. And if we rearrange the terms, we'll find that diameter of the dark ring is proportional to square root of n. N is nothing but a natural number. Whereas diameter of bright ring is proportional to square root of odd natural number. Here in diameter of dark ring, it is proportional to square root of natural number. And one important point what you have to see here is, if you see this interference pattern, rings pattern, as you can see, when your order is increasing, what is happening to all circular rings? They are coming very much closer to each other. So this is about our Newton's rings experiment. In my next video, I am going to discuss what can be the applications of these Newton's rings. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.